Hi folks, welcome back to MEAM 543. Let's start with a recap of what we did together in lecture last week. We took an energy perspective to think about how much fuel we need to have on board the aircraft when it's experiencing a given resistance to travel through a certain distance, which we call the range. We do a little bit of algebraic manipulation here, and a favorite trick when we do airplane analysis is to divide by the total weight of the aircraft, which is denoted W naught here. And then we also make the substitution that lift equals W naught when you're in steady cruise flight. So we get to this final equation, which is the fuel weight fraction, the weight of fuel divided by the total weight of the airplane. And we can relate it to mission requirements and simple design choices, or things that we can estimate from simple design choices. So as we'll see in our work this week, when we try to estimate the total weight of the aircraft to perform a given mission, we're going to need to know the fuel fraction. So this equation will turn out to be quite handy for us. Okay, let's say a quick word about estimating the total efficiency for propeller airplanes powered either by a piston engine or by a turboprop. The common assumption is to assume total efficiency is roughly constant between about 0.25 and 0.3, whereas in a jet engine, the most common assumption is to assume that efficiency increases linearly with flight speed, as shown in this figure from the book by Tornbeek. As far as lift-to-drag ratio goes, there are simple ways to estimate just from the aircraft type. This is a table taken from Wikipedia. If you match up the kind of airplane or the basic shape of the airplane with what you see in the table, you might get a decent estimate of an achievable lift-to-drag ratio in cruise. Most airplane design books will have a more detailed approach for estimating L over D max. Here's a graph taken from the aircraft design book by Dan Raymer, showing plots for different aircraft types, trend lines as a function of the wetted aspect ratio, which is a dimensionless measure of the span of the aircraft divided by the total exposed area. Okay, one challenge we have in the approach we've taken so far is when we get to a loiter mission, where the specification is more likely to be endurance or time in the air rather than range. If we just do a simple rearrangement of the equations, substituting endurance times velocity to get the range, we might conclude that the way to minimize the amount of fuel we need is just to fly as slowly as possible. But the physics has sort of changed on us, and as we start flying very, very slowly, the resistance force goes to zero, and we're not going anywhere, but we still need power to fly. So we have to do a little bit of algebraic rearrangement to get the equation into a form that we can use for hovering vehicles. And what we see is if we group together velocity and resistance force to form power, now we can include a general expression that gives the ratio of the power required to the weight of the airplane, and a typical value for that number is 20 meters per second. We'll have to wait till later in the semester to understand where this number comes from.